So, you want to build a Cray?
Yes.
All right. Let's see what's going on. So, what I'm going to kind of start with the end. And I'm a member of the knotsmakers.org, or Knots Makers group in Knoxville, Tennessee. And we have a Cray XT3 cabinet, and it's got XT4 blades inside at our makerspace. And so the last portion of this talk is going, how did we take this thing that had been surplused and bring it back to life? And so there is going to be some, how did we put Linux on that, and some other things like that. So, all right, but I also work at Oak Ridge National Lab, which most of you probably know is the home of, I'll still call it the fastest computer in the world. It's number 2 right now. The name of the computer is Titan, and it's a Cray XT7. It's the successor to a machine called Jaguar. I worked on Jaguar, so I'll often flip back and forth. Okay, sorry, going the wrong way. So, right? Okay. Okay, we'll learn this one. So let me give you some of the numbers to impress you. So in Titan, there are 18,688 16-core AMD Opteron processors for a total of almost 300,000 cores. Okay? There, for each CPU or processor, there's a matching K20X GPU. That's a computational GPU from NVIDIA. And each of those GPUs has a little over 2,500 cores by themselves. And if you multiply that out, it's actually a little over 50 million.
It's a big number.
It's a big number. There are 200 cabinets that compose this machine, and it has a theoretical max, if you could get all that going in the same direction, of 27 quadrillion floating point operations per second. Floating point operation per second, it's a flop. That's a 2.5 plus a 2.5 equals 5.0. That plus is a floating point operation. So writing it out, petaflop is what we call a quadrillion flops. And so this is a quadrillion. I had to, so thousands, millions, billions, trillions, quadrillion. Okay, so it can do, and we've demonstrated on a real problem 17 and change petaflops, but who's counting a trillion? Okay, if there's more at Oak Ridge. O.R. Nels also hosts the 2 other machines. Cray is owned by the University of Tennessee, and, well, there we go. Gaia is owned by NOAA. Both of these are in the top 50 machines in the world. Cray topped out at number 3, but it was a few years ago. And we'll go into what's number 1, number 2, number 3. What's that mean? But let me give you a little server room tour here. So this is walking through the server room where all these are. I don't know if any of you know Scott Milliken. Scott Milliken had invited me here to speak. He's the lab manager for all this room. And so this is what he does every day is watches these rooms. And so he had let us in, and little did he know what he was getting himself into. But yeah, this is Gaia from the side. And let me, each of the machines, you'll see this machinery, this stuff here on the left. We'll talk about that in a little bit, but that's really the refrigeration units for these things. That's looking down that they have corridors of these racks. And so actually, yeah, so you're seeing the back side of one rack and then the front side of the next rack going through.
So there's not back rack and back rack?
I don't think so.
So they don't have cool and hot aisles? That's weird that they wouldn't have that.
We do not And there's some interesting things.
They have refrigeration built into the racks.
They have refrigeration built in, and the refrigeration, they're actually room neutral. And actually they were room positive in terms of, or room negative. Anyway, when they replaced that first rack, or the first machine, the XT3 and the XT4 were air cooled.
Yeah.
And we'll get to what that meant to our makerspace, but these machines are water cooled, and they have refrigeration units at the end that chill the air, but the air coming out of the top is actually neutral or actually cooler than the incoming air. So I heard yesterday that they actually cooled the room for a long time using their new Cray whenever they got it. So it's quite an air conditioner. So here's Kraken looking at it. These are those are heat units going over or cooling units sitting up here. And so, now we...
Is that all of it, or is there more rows in there?
That's just the front row that I'm showing you. Gaia just has
How big is Cray?
Kraken's about 4 rows. It's roughly half of the of Titan, or it was roughly half of Jaguar. Let's see, that's the front of Titan. This is looking from that row to the back of the room, and it's hard to get perspective in here.
Sure is.
But you'll see those are 7 more rows of identical setups there, and so a total of 200 racks, we said. And then this is the very back of the room. You can see the refrigeration lines a lot better going over the top, cooling the racks. And
Is that him in the picture?
Scott was with me. This isn't Scott there. This is another couple friends of mine. Yeah, but we were like
You guys
Japanese.
don't know that's Dolomite. They might know him better by his hacker name.
Oh, okay. I'm sorry.
That's his street name.
But yeah, I took the guy in the lighter colors is a Pellissippi State local community college student that's been helping me out, and he was just all his geek dreams came through yesterday. He was just he got to go into see Titan, and then later we went to Buddha Cray. So it's very loud in this room. Hearing protection is required. This next one is a movie walking down the front of Titan. So I don't know. Anyway, it's just really loud.
It's fine.
I have a couple more. Yeah. Oh, handy dandy. Okay.
Press the button. Yeah, I was gonna say,
Oh.
just the audio before you plug that in.
Yeah, it's gonna get really loud. It'll be 1-to-1 match.
Remember the scene from Back to the Future?
Next.
Yeah. Okay, so we say it's the fastest in the world, but says who? And so there's a top500.org. It's the group. They've been listing the top supercomputers in the world for I don't know how long. It's a list that's published twice a year, and the rankings are by flops achieved on a matrix calculation, linear algebra, and a little hard to read, but Jack Donguera was the author of LinPack, which is the benchmark used. He's a distinguished scientist at ORNL and a distinguished professor at UT, and his signature is here. And it's one of the founding fathers of scientific computation. Currently, the Chinese military is ranked #1. That was a list that just came out like a month ago. It's issued twice a year. This is the certificate for Titan that hangs on the wall at ORNL. And so it's saying is ranked number 1 among the world's top 500 supercomputers with a 17.5 petaflop LIMPAC performance. So, okay, and so that's who says who. Gonna live. So this is my credibility. This is what I worked on Jaguar and now Titan. It's a model called Glimmer Sysm, and I did the parallelization for this. So it was effectively a serial or a scalar model that then we parallelized so it can run on any of the parallel architectures. It was parallelized using MPI. We'll come to, and so the ice sheet model, and so this is for land ice sheets. So think Greenland, Antarctica, big land ice, not sea ice. It calculates a set of PDEs, or partial differential equations, for ice thickness, movement, mass balance, all these different things. That's the mathematical expressions of the PDEs. For some of them, it's really Navier-Stokes. And then this is an example of some of the outputs. So that's all of Greenland showing velocities of different portions of the ice sheet.
Wrong, Greenland's much bigger than that.
It's not the scale.
I should put that at the bottom. I like the scale. Okay, so so for solving PDEs, I'm not going to try to stretch your mathematical remembrances very much. But the overall idea is that you do have this volume of something. And so you're trying to calculate the volume of, or not the volume, but a temperature field, let's say, over space. So 3 space, X, Y, and Z. And what you're doing is converting that through a stencil to calculating your derivatives and the X, Y, and Z directions. You calculate all these, or you write down all of these relationships between all the different nodes, and you'll end up with a set of indexed equations like that are you have to solve simultaneously across all those. Rewriting as a matrix, it simplifies the look. With PDEs, you often get this diagonal, everything else off of here is zeros. Yes?
I'll make sure grab the mic.
So when you were taking this to a parallel model, were you doing, was it the matrix algebra that was being parallelized? What step of this was being parallelized?
Sure. It was all the math, all the model had been done and proven for, small size.
Sure.
What it was really doing was splitting it up, and so that as far as each, and so what I was doing was taking that small model and replicating it thousands of times, and then handing each of those small models a portion of whatever ice.
Is the code open source, or at least source visible?
It is part of the what's called the CESM
Okay.
from NCAR, and that is
Right.
publicly available, but you have to sign a
Yeah,
license type of thing.
Okay. Cool.
Okay, that's part of that repo. Okay, so anyway, that's my credibility. So let's go into the components of a Cray. And so I heard some of you already saying, I am going to speed up my gaming system and get me a Cray processor, and man, that. And Seymour Cray was the designer, that's where the name came from, and the founder of the company. And a quote from him, anyone can build a fast CPU, but the trick is to build a fast system. And I heard you mention the CDC 6400?
6,500.
6,500, thanks. So he, before starting Cray, he worked with CDC,
Control data.
Control Data, thank you. Control Data Corporation. And there he was designing the fastest systems in the world, and he was meticulous about all the other pieces that go into making a system fast. You can make a really fast processor, but you can starve it in so many ways that your throughput is nothing. And so that was his thing. 1976, 5, 4, somewhere in there, early 70s, he was at CDC. Let's see, and you guys look like an audience that can appreciate some vacation pictures. So this is the Cray one, serial number 3. It is at National Center for Atmospheric Research in Boulder, Colorado. And last summer we were in Colorado, we stopped and saw the Cray, so that's my family standing in front of that Cray. It's still on display. It was delivered in 1977. It was almost $9 million. I like this, $7 million for the machine, plus $1 million for the disc. That just cracks me up for some reason, like, oh, you want a disc with that? You know, I don't know. This picture of the DOS disc coming with it, and it's like, anyway, they priced it like, maybe we'll sell 10, you know, and so that's why they were price crazy. And they ended up selling over 80, and it was at least twice as fast, and maybe I think it was like about 4.5 times as fast as the CDC machine at the time. So some of the other things that you can see in this picture are, this is the cooling built around the bottom in this bench down here, and so Cray integrated cooling as part of his designs. And then this is basically memory. It's just sticks of memory, and it's packed really, really tight, and they're just stacked up inside of there. And it was one processor, but it was, we'll see the specs here on the next slide. I don't know if you guys can see this.
Comparison.
All right. And so what I'm replicating here, this is another poster at in-car, and so this text down here is comparing the Cray to iPhone 3G at the time. But I also wanted to point out this picture here. It'll come back up in a little while. There's about 5 or 6 guys pushing this machine around. So you can maybe imagine where this is going to come up later. Seymour Cray is pictured in here. He's that dot right here. Okay, so 80 megahertz clock speed. It was a balanced vector processor and scaler. And so a lot of the machines could do one or the other at the time, but not both very well. Or they had really deep pipelines or whatever, couldn't switch. So it was 1,064-bit words of memory. So it was 64-bit. Whoever was saying 60,
Yeah,
you were right.
That's
Okay. Okay. Could have been.
The 6500 was a 60-bit word.
Okay. So it could achieve 80 megaflops. It could do that, and then peak it could go up to 160 megaflops. So that's 160 million floating point operations per second. It weighed 5.5 tons. That's kind of why I like this picture up here. These guys pushing it around, and and iPhones 1.46 times 10 to the -4th tons. In case you were wondering, that was kind of fun to work out this morning. Okay, so on processors, Seymour Cray held that computers should obey a square law. When the price doubles, you should get at least 4 times as much speed. He really had this bias. He wasn't done until he could deliver with each generation 10 times more processor performance. And that actually drove a lot of his companies and corporations into the ground. Okay, very good.
He went broke at least 3 times.
It's a really interesting history. He's a neat guy. Go look up the article on Wikipedia. And his drive to deliver that performance forced the company into really exotic research, and so they were the first looking at gallium arsenide, for instance. Now the processors are AMD Opteron, 16 core. They're big. Not a lot of us probably have them, but we could go get them if we wanted to. So they are a commodity. Let's see. So another thing about Cray was that he resisted the massively parallel. And so there's another quote from him: if you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens? And I think I've seen that recently on like Google Plus as like a question or something. That
Was it due to complexity that he didn't like massively parallel, or why did he hate the future?
He was very, so he was a designer, he was the architect. And yeah, this kind of 1,024 chickens is kind of, he didn't like, he wanted those horses. Okay, we'll try this one. Okay. And so it was his personal bias, and it was just something that he could not get around, and it took a long time for him. He's
been dead 15 years.
Yeah, it was the mid-90s, 96, I think is when he was killed in a car accident. By the mid-90s, what had been catching up was compiler technology, because it was phenomenally difficult to program anything, and then trying to program 1,024 chickens would be a lot harder. But by the mid-90s, compiler support was catching up.
Yeah.
Getting better. Okay. And so in the mid-90s, he started a new company to design his first massively parallel machine. And there again, true to his design, his architecting, he wasn't focused on the processors, but he was focused on all the bottlenecks around it. The communications, the memory, bench, or performance. And
That was no small part of it.
it was not, still is not, and that still remains a focus of Cray. So getting to massively parallel. Mainly, well, this is diving down through history and really going through processors. So we all know we've got a processor, we've got a computer, we can make it do something. And then a lot of us had dual processors. So it's like, but you really kind of could treat it like 2 computers and it was just in the same box. And so computer to computer, I need to tell you something, you need to tell me something, then that's handled through something called MPI, or Message Passing Interface. And it's libraries, it's function calls, you can go download it, you can read the book. And Jack Dongera, it's not too bad. I've read them. Jack Dongera this was a big project of his also. And but then something happened. We hit the gigahertz wall, whatever you want to call it, and we just, you're hitting a thermal barrier, you're hitting a lot of things. And so our CPU manufacturers started multiplying cores. And but cores aren't computers. And so what you're speeding up with the core, or what you want to do with the core, is threads. And so you're doing threads, you want to split up, and so then all 16 of your cores can go running off doing something at the same time. So you've got parallel inside of your computer, inside of your CPU, and so there the techniques are threads, fork join, that kind of thing, and the library is called OpenMP. And it's really not a library, it's a compiler extension. And so you're putting comments in that you say, this next for loop, do this. You can split this 25 ways if you want. Well, some more vector units. And so you're splitting out. So that has to do with your floating point operations. And so many cores can have multiple vector units with them. Well, if you're trying to stream vectors and do calculations, then, so think vectorization, SSE, extensions, that kind of stuff. Again, it's it is CPU instructions, but also you're really still looking at the compilers. GPUs have thrown another wrinkle in there. A huge, an immense wrinkle for us scientific, computational scientists. Yes?
How would FPGAs stack up in this, with vector math? It should, that's my research, that it does. I'm thinking specifically support vector machines.
Okay. I know the term, I know of it, but I really,
It's a regression model.
yeah, later.
Think regression.
Let's,
Yeah.
I've got friends that love FPGAs, and
Yeah.
and they would probably love to talk with you too.
All right.
But it's less a specialty of mine. So GPUs have thrown a huge wrinkle. It's like making us rethink all this again. But think about what you're throwing away. If you've got your serial program that you rocked, the Cray 1 or whatever, you had that serial program massively parallel, split out. Okay, well, 2 CPUs, that's okay. You got along. Cores, well, I'm just going to ignore them. Well, now you've thrown away, a good, some multiple of that machine's performance. You said, oh, I don't have any vectorization. You're throwing away another multiple of the machine's performance and so on. And GPUs, well, they give us a lot. They're very different to try to get a hold of. And there, CUDA, OpenACC is an extension. OpenCL is another. OpenACC's directives very much like OpenMP. Okay, I had debugging, profiling, challenges that you face when you're doing massively parallel. You're doing tens of thousands of processes, a lot of, that'd be quite a lot for Visual Studio to split out your debugger. They're specialty software and support so that you can be assured that your calculations are doing what you want them to do. And the word that comes up in all this is scalable. Problems or algorithms that can effectively use this massively parallel computing. So for summarizing the parallel, I like in 77 is when Cray delivered the Cray 1A. In 78, the Cray operating system used to be programmed by Cray. The the first automatically vectorizing Fortran compiler was delivered in the Cray assembly language. And Cray's had a long heritage in the compiler technology. They're still tuned to their machines. They still do a lot of development in compilers, but they are tuned and applicable only to a Cray. They remain cutting edge, taking the performance technologies, but I've got a GPU system. We can get awesome performance on the problem on a Cray, but it has to run on Windows. And we're like, do you all have a Windows edition of your Cray, maybe? And they don't, but I would sure love one. I've already mentioned MPI. OpenMPI is an open source version. MPICH is also open source, freely available.
What's open source?
OpenMPI.
Oh, yeah.
Okay.
CL, yeah. How do you like MPI versus CL?
They're actually different critters, I think. But let me.
Yeah.
Anyway, OpenMP, pthreads, and that's really where we're living in terms of our CPUs and our computers is at the thread level, and so .NET language, really Intel. Most of the industry is here dealing with threads. The other things are free, CUDA, GCC, and so on. But moving along, massively parallel machine, lots of processors. I like that we had our. So how can we network and communicate between all these nodes? And so thinking we've got the NSA proof telephone design here, and so you can string out, right, one to the next. And what you need to be able to do is to easily, I need to add another cabinet. Well, this design certainly comes to mind, that would make it really easy to join in, but if this guy needs to get a message to that guy, it's got to go through a guy in the middle, and that's a lot of strings and tin cans. So the next design, all these designs were tried over a period of time that nobody knew what to do right. And so they were just trying anything. This was kind of I was trying to diagram what's called a fat tree. And so down here, these guys can communicate. As you get closer to the root, you make the bandwidth fatter. So then you can have constant up and down bandwidth between the processors and still be able to join things together. In the middle is a hypercube. There were a hypercube, or that's a 4-dimensional cube.
How do you do that connection?
Well, hold on. And so, there were all these different designs, and we're actually going to do an exercise here in a few minutes. A completely connected, because then you could say, well, this should be the best, right? Because now every processor is only one hop away from you. And so that should be the right design. But it's immensely complex to add a new machine. Every machine you have to completely connect it to all the machines that were there before. But it was a lot of machines, a lot of companies. But I promised an exercise here. So Cray T3D, late 90s, 98. The T3D stands for three-dimensional torus. And so bonus points if you all knew that torus is the mathematical name for the skin of a donut. Okay? And so this is a three-dimensional torus. Everybody see the donut in the diagram?
No part of it.
Okay? All right, so think of the grid, the layers, okay, running this way. And so just an XY grid, all these connected up. And now I'm going to put the mic down to do this. All right, I'll try to talk loud. Okay, so we've got the grid laid out like this, all right? Now what we're going to do is join the edges, because whenever you get to here, well, what do you do with this dangly bit? Where's this wire connected from this guy? What you're going to do is loop it around to the bottom. And so by doing that, then I've connected the wires top to bottom here. Well, then I'm going to, if you loop it around, then you would get a donut shape, okay? What I've done with that is just one layer. So now think of lots of layers, and so you're trying to solve PDEs in three-dimensional space, right? So you're going up, down, left, right. It's YZ, okay? And so do the same. We've got the top and the bottom. All right, so we're going to join
You got a
the
mess.
X, the Y. So let's see if I can keep the top visible here. So we got the X and Y. And now what you need to do is reach into four-dimensional space and just pull the Z around and connect it.
Where's the fourth dimension coming from? Is it because there's
It's-
multiples of these?
Yeah, and so what you're needing to do, X and Y would make
So
a
it's like-
bunch of donuts shelled inside of each other, right?
Okay.
But in four space, if you think like a mathematician,
Yeah.
there's another, the top and the bottom would be free just like these are,
Right.
whenever you're joining them. But you can't embed this in three space.
Right.
So that's, it wasn't quite a hypercube. Hypercube's a four-dimensional extension of a cube.
Cube, yeah, great.
Okay, and so then but you can see the efficiency for PDEs is that very often you need to talk to your neighbors north, south, east, west, and up and down. And so that's the communication flow that transfers, that works well. Okay. Those are the types of problems often solved on the Crays, are the fluid dynamics type of problems. Let's see, and so summarizing the interconnect, C-star was their previous technology. Gemini is its current technology. The Gemini for the Cray is represented here. It's showing very fat pipes in different directions, and so it was an upgrade to the C-Star. And but these interconnects are exotic. They're unique to Cray. You couldn't just get one and hook it to your PC, and it wouldn't make any sense. But something I learned while putting this talk together from the person who owns our Cray at the Makerspace is that I was griping about whenever I was working with Jaguar, and then it would be like, ugh, it stopped. Ugh. And then you would have to wait a couple hours, and then it would be going again. And what he said was that whenever the C-Star had no recovery. And so whenever you like dropped a node, something went with one of those chips, then you lost the whole machine. You lost the whole topology. No more communication could occur. The only thing to do is go and like pull the plug and restart it. Gemini can reroute and recover. And so it can flush the network, get it back to a previous known good state, route those out, whatever was failing, and then recover. And so it added robustness, and as you go massively parallel, you've got to do that. But overall, the GigE switch for most of our calculations is good enough for us. We can all get that. A few more components. Moving along, data storage. So interesting things. So the compute nodes are effectively net booted, and they run from a RAM disk. They don't have any hard drive. I got into the word huge here. Huge data sets are required for initial data. So when you're trying to get that problem started, you've got all these processors and they're ready to calculate, but they need whatever they need to calculate on that initial data. You've got huge output, and so you've got throughput. If it's all waiting for data to be written to disk and you're just sitting around, you're getting no throughput for your through your machine. And then, it's a huge potential bottleneck. That initial data loaded across all the compute nodes. So imagine 200,000 computers just sitting around waiting for the hard drive. We get frustrated when one computer is sitting around waiting for the hard drive. 200,000 all waiting for it. So the solution, it's a very active area of research. What you want is a parallel file system. And so you want like one file open with 200,000 processors, and all of them can pull in at the same time their portion of these huge files. And so Luster is the name of the file system we're using at Oak Ridge. And we'll have a picture here on the next one of our file system. And so the current file system is 14,000 SATA drives. It is a RAID 6 technology or redundancy, and so you've got 8 disks plus 2 spare. And I asked yesterday, so there's 10 to 20 hard drive failures per month, which I thought was remarkably low. Just 14,000 SATA drives. They said it's been ticking up. This is about 3 or 4 years old, so it's starting to tick up. It's being replaced. And so this is a picture of the new system. There's a little over 20,000 2 terabyte SAS drives, storing a total of 32 petabytes spinning. Okay, so and a 1.2 terabyte per second transfer rate. And this is I call it beer cooler, but yeah, they push the cold air up through here and then it exhausts out through the machine. So this is a cold environment, and then the room's not all air conditioned, cooled. It's really cold in this room. And so these are just hard drives. And I got this picture when we were in there yesterday. This side's the supercomputers. This side of the room, see these pillars, is all storage. And I wanted to give a different perspective. This is from the outside of the room. And so if you go to the NCCS to observe the computers, there's the pillars. You can just barely see the top of the computers there. And the other third of the room is just hard drives. It's just data. And
How many megawatts an hour does this thing burn?
How many power plants? Well,
yeah, same
No
question.
answers. Yeah.
We're going to actually answer that. It's a fun, I was curious too. Okay, so we'll finish up a couple more components here. So programming, operating systems. We've gone through a lot of it, but so Cray OS was proprietary. It's now Linux, SUSE. So it's a version of SUSE Linux. It's been modified, the network stack especially has been changed, and so it's called Cray Linux environment, or the CLE. Yeah, so Cray compilers, there's also other companies that operate in the high performance computing realm, PGI or Portland Group. It's a compiler company. Intel is more pushing down towards the threads. They're not really helping us a lot in these crazy rarefied air environments. Libraries, we've talked about a lot of these, so CUDA and so on, and the debugging tools. And this is my favorite out of all of them. This is called Vampire. It's from a university of Dresden. But what you're seeing here are MPI communication patterns going here. You're getting a visualization of, oh, wait a second. You know, my computer's sitting idle for all this red time. How can I get it to computing? And being able to look and visualize across all those thousands of processes. Why am I getting,
So you
how
have-
could I improve my performance?
You have GCC compilers. Is there anything for LLVM, or is that totally outside the space?
It is not outside the space, and there's,
The LLVM seems to be taking over the world right now.
yeah, let me think about my answer to that one.
Okay.
I would love, because there's, yeah, so you can do GCC. What we've done a lot, one compiler won't find something that another compiler will. In GCC and G-Fortran,
Yeah.
do a lot of Fortran programming. Fortran rocks, okay? So that's, a lot of the programming, scientific programming, is still done in Fortran. Now that somebody asked about power cooling and infrastructure, I'm throwing them all together to get through them. Integrated cooling, again, was a Seymour Cray design feature. He integrated it from his earliest designs, and Crays will not operate. They'll check the environment, they'll come up, and the very first thing they'll do is check that environment and make sure that the environment's satisfactory to whatever it needs. And there's an environmental interlock. They will not run if, you know, it loses air conditioning or whatever. And Cray knew he needed to shut his computers down if he lost cooling, but he didn't have the interlock the other way. And so there is a story of a frozen computer that they lost power. The computer stopped computing, but the cooling didn't. And so whenever they came in the next morning, they came into a frozen ice cube of a Cray. Somebody asked about Cray or power. 8.3 megawatts was used for the LinPack whenever they did their LinPack top 500 run.
Right.
So everything's lit up and running. So if I did my math right, okay, 8,300 kilowatts times an hour, and so 8,300 kilowatt hours, hopefully. I don't know how much they pay. Our industrial rate in East Tennessee is about 13 cents per kilowatt hour. So that's almost $1,000 or $1,100 per hour power bill, multiplying it out $26,000 a day, and $750,000 per month just for power for this. What has become much more concerning, important is the thermal efficiency. How much are you getting? How much computing are you getting per watt power use? And Titan actually ranks like number 2 or number 3 on that list. So it is very efficient, but it's huge. And power is really also a constraint to exascale. What comes after petascale? Exascale. An exaflop is a 1,000-fold increase to a petaflop. Okay? And so if you just scaled all your numbers, then you're needing 8.3 gigawatts, and that is multiple nuclear power plants to power your one computer. Yeah, we haven't said anything. Infrastructure, the maintenance, all the space, all that stuff. So there's a lot of costs that go into it, and so people often ask, well, why'd you have to retire it? Why'd you have to turn it off? And so that can give a reason. So summary, Crays are wonderful machines, but they're designed for a problem set that not a lot of us have. There's several exotic components, but the ones that impact us are commodities. And our phones and computers and all the things we have are wonderful little parallel computers. You can get into parallel computing that way. I did. Programming, did my PhD research on my Mac 8-core machine, and that experience translated clear up to running on the Cray. And so most of the software and resources used on the Cray are freely available. Anybody can get them. Building your own Linux cluster is something we can all do. This is an example of one. I had 2 high school students over the summer, and we rehabilitated an old just a Linux cluster. It's about 30 Dell 1850s. They're older machines, and they can max out at like 3 gigs of memory, but they still make a decent compute.
A parallel computer environment.
Yeah, parallel MPI computer environment. So we talked about the big Cray. Let's talk about the Cray at the makerspace. So here it is, pictured. And I've got the front cover off so you can see inside. What there are is there's what's called 3 chassis. And so these run these ways, this way, so 1, 2, 3. And those are like 3 separate racks, sort of. There's 8 blades per chassis. And then inside each chassis, there's 4 nodes or 4 modules. And what these with the holes on them are kind of the I/O nodes or the startup nodes. And so you're seeing the wires going in. Out of this chassis, only the bottom row is fully populated with memory. And this is, we said it was net booted. This is an Asus desktop machine that's providing the boot and root and all the management of the Cray cluster there. Let's see what else. Above that is an InfiniBand fiber optic Cisco switch. And so there's a total of 96 nodes per cabinet. All right, so what do you do with one of these when you win it at auction? Well, it did sit in their garage at their house, and he did have a Cray in his garage, and he did ask his wife first before winning the Cray. It weighs 1,500 pounds. It was bought at surplus for $750. And I promised a little story. He told me, he said, it took 8 guys to push it onto the moving truck. And so that reminded me whenever the other guys were pushing around the other Cray. He said they were a lot smarter when they got to home. They took all the blades out, took all the sides off, and then you just had like a 300-pound rack that they could go down the ramp with. So there was just, I didn't know anything about the Cray being bought, that he was going to try to move it to the makerspace or anything, until there was just this explosion of just really arcane, weird power discussion that came up on the email list. And they started talking about 3-phase, and well, how many amps can you get out of a blah, blah, blah. So it turned out that this was the discussion for how do you power a Cray. So it is 3-phase, 208 volts. We needed an electrician to come and install that. They spec that they want a 100 amp circuit. Try to get an 100 amp circuit from TVA. We have a 30 amp circuit. And this is the power module at the bottom. and it delivers to the machines. It's delivering 52 volts DC at 62 amps. It uses about 3.5 kilowatts just sitting idle. And so it costs us about 60 cents an hour to run. I was like, that's not bad. And then I multiplied it out, and it's like $15 a day. Okay. But then it's $400 a month. Yeah, I was like, oh. And that's not including anything else. Okay, so cooling. So another of the discussions that was going around was how are we going to cool this thing? And it's like, well, we could use a single-phase car fan, you know. And so there were just all these crazy things going around. We were able to use the original 2,200 cubic foot per minute fan on a 3-phase motor because we did get 3-phase power. There is a 15-degree Fahrenheit temperature rise between the incoming and the exhaust air. And so I multiplied out, well, we have 25,000 cubic feet space at the Oak Ridge Entrepreneurial Center where we're located, and so we can turn over all the air in the room and heating it up by 15 degrees in 12 minutes. All right. So this is a compute blade, and I have one up here. I'll hold it up here, and y'all can come and see it. I'm trying to get to the end here. So the C-star interconnects are down here at the end. Memory slots, and then 4 CPUs. These were only single CPU machines, the 4 modules. But notice what's not on here. You don't see a lot of other support chip anything else. Yeah, this is a remarkably, I'm going to pick this up. A remarkably clean board. Okay? So, that necessitates that you have to push everything to the board. Everything goes over as you're trying to boot it. These are the interconnects in the back. You open up the back of the Cray, and there's all these wires. Looks like the Borg or something. And you can't really see it, but these are labeled X, Y, and Z. This is where you would wire to the NetSky to create that 3-dimensional torus. That's all the communications power and stuff. Well, no, the power is that blue ribbon going up the side, is the DC voltage. That's just communication lines going through those umbilical cords. So here it is. Again, a couple more publicity photos.
Is there a control blade, or how do you get a terminal?
Starting it up. Okay? Good question. All right. I've got 30 seconds to do it.
You're good.
And then we hear, are we getting sound anywhere?
Yep.
Okay.
Yeah.
Start over, yeah, here we go.
Okay. This video is about 2.5 minutes long. This was from very initial, just clickety click, telling the chassis to start its power up sequence. The fan's coming on, as you see by the indicator, and you'll start seeing these are the control nodes down in here. And so you're going to bring up one while we're waiting for the lights to start going blinky blinky. A few other notes are that this one takes about 20 minutes to boot.
Yeah.
Jaguar took an hour to boot. It brings up, what they do is they have to push all of the BIOS, all of the boot, they have to bootstrap it in 4K chunks to one node. And they'll bring up one node, that takes an hour. And Titan now, because of all the GPUs and extra checkouts, takes 2 hours to boot one node. But it takes 30 seconds to boot the next 18,000. So, you know, it works out on average, not too bad. But are any lights blinking yet? Please, come on.
Yeah, a little bit.
We've got a few. We'll get there's a row of lights after. All it's doing right now is checking the environment. You know, I kept like, all right, we got lights. Whew. Okay, good. And so it's really just going through like all the hardware here, what's going on, hey, are we gonna run? I don't know, well, I feel like it, yeah, let's do it.
Woohoo!
And
Hello, world.
I kept thinking, all right, are we done yet? Okay, and then he's like, no, it's like you've turned your car on and it's decided that it is a car. But you haven't started it. You haven't gotten there yet. You know, it's just kind of checked. And okay, so that fan's pretty quiet. We're going to do another video. So now the blowers come up and then that's full speed. So this one's not very long. That's about finished. Okay. Here's a few of the screens. I'm sorry they didn't translate. You can come up or don't show up clear, but it's basically the commands to start powering this baby on. You can see its reflection there in the glass of the owner. We're at another stage. It has reported the machine's there. And let's see, I think I've got, basically this should look a lot like a Linux boot window, sort of. And you're seeing a lot of timestamps and things going by. So it's booting Linux.
Okay, failed.
Yeah. And here we go. I hope this one, I'm actually going to try to do it from up here because it's important to get this last part. Let's see here. Okay. So the last video I have. Okay. Here we go. Listen carefully. Okay, I don't know if you guys, did you hear it?
He said we're booting.
We're booted, and you hear me in the background go, huh. So, with that very profound announcement, what's that? Sorry. With that very profound comment from me, because I just, we're booted, huh. Okay, so,
You had to be there.
with that very profound insight
I
that I
like the
provided.
big crescent branch behind your,
You like that? Okay.
on your
So-
picture there.
Oh, good. So anyway, all right, so I'll call for questions.
So how do you control it? You have like Telnet serial console on it, or
The,
I saw the Mac, but like,
yeah, the only machine over here that the controller is this Asus desktop. So we've.
so it is just a machine.
It's just a machine, and then you're telling instructions to the chassis. There are microcontrollers in the chassis for environmental, all that, and you're actually bringing up 486 controllers on each of like the chassis being the horizontal thing. So there's a 486 there. Then you get to start booting the AMDs and the blades, and so then you get to we're booted after 20 minutes. Yes, over here.
In the hackerspace build, what are you using for your data storage?
It's actually in that he's using that Asus, and so there is that's a component he didn't get was the like the storage something
Imagine
unit,
that.
and so
So what is it, like NFS or something?
there's NFS, there's things yeah, and so you're doing that. It's InfiniBand is coming back. It's yes.
So, I mean, in the age of these commodity superclusters like Hadoop and a lot of the others, do you think there's still going to be a place for these bespoke machines for too much longer?
It's a good question, and you know, we keep making them bigger and faster, and getting bigger and faster problems, and or problems needing bigger. And so there was like a supercomputer collapse in the late '90s that a lot of companies went bankrupt. But they're exotic problems, you know. And so it's a great question. It could be subject to a lot of discussion.
It seems to me that as far as corporate is concerned, they're going to go down the Hadoop train.
Yes.
As far as scientific computing, well, so a lot of those problems, I wouldn't want to put those through a map-reduced process. It would be adding unnecessary complexity.
Yeah, and so business problems do not necessarily map into Cray space. They are They are esoteric that way. So, but we do still have a lot of big national, international importance problems that need it. Yes.
What was the smallest like problem set that's like gone through one of your clusters and like the longest like time running wise? Is it like somebody jumped with like a 5-minute problem, like because of the load, or?
They are shared. So that's something about it is queuing.
Really?
And that's because it doesn't make sense to have this humongous machine and you've got one guy running one processor and doing hello world. Okay? And so what you're doing is that there's a queuing management system. So then you submit and you say, I need 1,000 processors. And believe it or not, you'll get it back. I run up to 20,000 processors interactive on my code. And it allocates out of the giant pool, it will allocate 20,000 processors, and then you ask for an amount of time, and then you have it, and then when your time's up, they all go to somebody else.
Was it EQS or something, the queuing system?
The queuing system, Torque and Maui is used. That's partially open source. There's so Torque, Maui, Cray really has their own queuing system, but it maps just like open source ones are available. So if that helps anybody, yeah, it does an amazing job of being able to allocate all these resources and get your code over there and somehow map that. Well, here's your scratch disk space. Put your data here. These things can see the data, and the blasted thing works. It's amazing. So.
Is there much documentation available for the architecture or methodology behind the interconnects? And if not, was there an NDA signed when you acquired that?
This blade? This is out of the makerspace one. You let me bring it over here. I'm sorry. He said, I can handle it. Y'all can come and look at it.
Yeah, and if he's under an NDA to...
No, but there are licensing. And so he has a hobbyist license as a Cray. You're a hobbyist owner of a Cray. And so he had to have a hobbyist license from Cray for him to get the software for his Cray. So I do find that funny. All this stuff is talked about in the literature. So Dragonfly, he said, is the net's network topology. And so before we had up, down, left, or XYZ topology, Dragonfly has smaller pipes going around, but then it goes in more directions. And so he said that's becoming, we're moving different sorts of problems than just the classical fluid dynamics PDEs onto it. One of my other favorites is that Megadroid. Somebody's booted 2 million Android kernels on Jaguar and then simulated a whole city of Android phones all moving around, and they were sending text messages to each other and talking to each other and moving around and, hey, how are you? And so that's another, but it's a totally different problem than a fluid dynamics problem.
Sure.
So, anybody? Okay. All right. Thank you very much.
Thank you.